So first of all, BJT symbols, they look a little, not exactly the same as MOSFETs. The arrow tells you the direction of the emitter current. You notice with the PNP, the emitter is on the top, and the current goes into the device from the emitter, and then with the NPN, it goes out of the device to the emitter. So that's really the only difference between them. Literally, the only circuit analysis different is the direction of the current. It's not like a MOSFET where you have to worry about whether you take the absolute value of something or whether you do this or do that. You just look at the circuit and use what you know about it. And what you know about it isn't so much yet, but will be more. So first of all, when you put these into a circuit and you power them so that you have the base emitter junction forward biased and the collector base junction reverse biased, you can do that with two voltage sources, and you can have voltage across the PN junction that's forward biased, which in an NPN is the base emitter junction, and that will look pretty much like a forward bias diode. And then the collector base junction ends up being like a reverse bias diode. And that really pretty much holds true for the PNP as well. It's just that the subscripts of the voltages are different because the current is going the other way. But that's literally the only difference. Active mode is the mode that we use for amplifier circuits, and if you want to send something through the circuit. Saturation mode is also useful for different applications. So when we use those, we have kind of a different set of voltages we use for saturation mode versus active. In an NPN, we assume the base emitter voltage is about 0.7 volts, whether it's active or in saturation, because that junction is going to be forward biased no matter what. That junction, if it's not forward biased, the transistor's not really doing anything. So that will be, unless it's, the reverse biasing of that junction puts it into cutoff and there's no current flowing. If you have the device in active mode, the collector emitter voltage will be not huge, but a voltage, not fractional. If you have it in saturation, the collector emitter voltage will be about 0.3 or 0.2. 0.3 is about the edge of saturation, and then 0.2 is about as small as it ever gets. And when that happens, you have the maximum amount of current flowing through the device, and because the voltages have to add up, the collector base voltage, the collector will be about 0.4 volts below the base voltage. So it will be significantly different. And with a PNP, you have exactly the same thing, just flipped over. The only difference is that the collector emitter voltage will be, you'll either do base emitter is negative 0.7 or you'll do emitter base is 0.7. So that's really, again, the only difference. Everything is flipped over, but it's really pretty much the same. Oh, that's interesting. So as a summary, and this is not the end of the lecture, this is just a summary. Sorry. There are ways to calculate the voltage and the current at any given point based on how when we looked at diodes, kind of based on how they work. You have the exponential function. So the collector current can be found, if you know the saturation current, then you just take E to the VB over VT. That's pretty much exactly how you got the current in a diode, because a PN junction is like a forward bias diode. The base emitter voltage controls that, so you can find it that way. IB and IE, you found pretty much the same way. It's just that the saturation value is divided by either beta or alpha, depending on what type of device you're looking at. The thermal voltage, Generally in here, we use 25 millivolts because it's pretty close to room temperature. Sometimes 26 millivolts is used. That's good if the temperature is 300 K, which is a little hotter than what normal room temperature is, but it works as a nice round number for other classes, not so much for this one. It doesn't matter to me which one you use. If you don't use 25, you'll get a slightly different answer than what I get. I generally try to use 25 in here to just keep things consistent. If you look at what the graphing looks like, you see that if you graph IC and VBE, it looks like a forward biased PN junction because that's what it is. So it looks just like a diode. If you change the temperature, you get different values depending on what happens. If you start at a temperature that is kind of a normal, I guess, temperature, let's say you start out with T1 and you decrease the temperature, so you come up with a second value that's less, the curve actually kind of moves out. And the same thing happens if you add a third one. As you decrease the temperature, the whole curve kind of shifts for a greater value of VBE needed to make the same amount of collector current. That's basically what that does. Yes?
So in modern applications where, for example, like in a computer where it gets stupid hot, how does the system correct itself for that?
That's why you have cooling fans and such.
Yeah, but I mean, the difference is still huge.
But you would use also, you would use different, you wouldn't use a transistor by itself in something like that. You would use an integrated circuit that had everything built in and was already designed for the temperature in which it's being used. So that's basically the temperature range in which it's used is taken into account in the design. So this will look familiar because if you graph the different values of VBE and you increase VCE, you get curves that look just like the MOSFET curves we used. And you can extrapolate those back to a voltage, just like we did with the MOSFET. In fact, the extrapolation back was first done with BJTs. So that voltage, V sub A, has a name when we apply it to BJTs, and it's called the early voltage. And it's named after someone named Early. It's not because it happens earlier than everything else. It's just named after someone. And he was the guy who discovered this relationship, and then they realized, oh, the same thing happens with MOSFETs. But it's for a completely different reason that this happens. In a BJT, the tipping up of the curves happens not because of a channel length modulation, because in the MOSFET we had a channel and the length changed depending on what was happening with the VGS. There we go. I have trouble when I switch back and forth between MOSFETs and BJTs, which drives me nuts when I'm doing semiconductors, because now I'm doing MOSFETs and semis and I'm doing BJTs here. And then next time I'll be doing BJTs in both. So, yeah. Anyway, this is caused by the width of the base depletion region changing. So something is changing for a similar reason from a similar, I guess, has a similar result. And so we basically most of the time ignore this. But in order to account for the fact that the curves tip up, we have to change the collector current equation a bit. And all that's doing is accounting for the fact that for different values of VBE, you will have different base width in the depletion region at the base that changes. The slope of the curves is the inverse of the output resistance between the emitter and collector. That's just like with MOSFETs. The slope was the inverse of the output resistance between the drain and the source. So again, it's pretty much set up the same way. The math for determining RO is a little different, but not terrible different. So in order to find how to get this output resistance that results from the fact that the curves slope a bit, we take the partial derivative of the IC equation and we hold VBE constant. So once VBE is a constant, it's not part of what we have to worry about as such. So we take the original equation and we're just going to take the partial derivative of IC over VCE. And when we do that, the only variable we have is VCE. We're actually going to pull ISE VBT over VT out of the equation just to get rid of it. And then go ahead and take the derivative of the inner 1 plus VCE over VA. And if we take the derivative of that, we just get 1 over VA because the VCE goes away, the 1 goes away. So we end up with 1 over RO is ISE VBT over VT times 1 over VA. Then, since the original collector current is that exponential function times 1 plus VCE over VA, we can put IC on the top and then put that 1 plus VCE over VA on the bottom, and we will have a proper equation. So all I did was take this whole thing here, and this part relates here, and then this is on the bottom to make ICB on the top. Once we've done that, we can multiply the lower part through by VA, and we end up with IC over VA plus VCE, which is very similar to what you did with MOSFETs. In fact, if you have VCE a lot less than VA, you can calculate it pretty much exactly the same as you did with MOSFETs. And you're just using collector current rather than drain current. I know that I pretty much every semester ask a kind of a question that deals with that, and some people use the exact and some people use the approximate, so there's always going to be 2 technically correct answers. So it doesn't really matter to me which one you use. The answers are slightly different, but they're not terribly different. So models, we have to look at models. We looked at some last time. We have to add RO into the large signal model. And when we do that, it just ends up going between the collector and the emitter. If you have a circuit in which the emitter is grounded, RO ends up being in parallel with everything else, just like with the MOSFET. If the emitter is not grounded, it becomes a bit more complicated, but basically when we get to AC stuff, the models will look similar. We'll have 2 models and we'll be able to adjust for that. So this is the model we use if it is a voltage controlled current source, and then this is the model we use if it's a current controlled current source. And we mostly use this model versus the voltage controlled, because it's going to turn out that IB is a lot easier to find oftentimes in bias circuits than VBE, so we end up doing that. So we can put that in. We can also do this with a PNP, and there is also a current controlled model for that, but you can use your imagination to figure out where RO goes. So what the result of this is, that this output resistance depends on the value of the collector current, and it changes as the collector current changes because VA is not going to change. That's going to be the same. So if we have a BJT that has an early voltage of 100 volts and we want to look at what the output resistance is at 3 different values of IC, we're going to assume VCE is much less than VA, so we're not even going to use that. And so if IC is 0.1 milliamps, then RO is 1 megohm, which is actually really big. It basically has no effect on the circuit. You can put something small in parallel with it, and it'll pretty much not have an effect. At 1 milliamp, then it's 10 times smaller, so you get 100 kiloohms for that value, and for 10 milliamps, you get 10 kiloohms. If your RO is 10 kiloohms and you add a 10 kiloohm load, you're already changing the resistance out. You're basically halving it. So As the collector current increases, the RO value will decrease and have a greater effect on the circuit. So that's one of those design things to bear in mind. The characteristics that I showed you initially were based on differing values of VBE, which is similar to what we did with MOSFETs, with differing values of gate source voltage. But that's not generally the traces that we use. Usually, because the IB model is easier to deal with, we usually look at the base current and change that and looked at the collector and the collector emitter voltage that way. And we end up with characteristic curves that look similar, but are a little more easy to deal with. If you use a curve tracer, of which there's one, I think, upstairs somewhere, that's basically what it will give you. It will give you traces like this with the base current being the control, and then it will test VCE and IC. In the active region, we generally want the Q point to be in the middle, just like we did with MOSFETs, and then the values of IC and VCE are just found by going over, and then the current, the base current, is whatever line you're resting on. So this is a circuit that is running IB3 as its base current, and then it has a value of IC and VCE based on that as part of the curves. Beta values can change a bit. So I'm going to talk about them a little bit. Most of the time we're not going to worry about it too much, but when you have a particular Q point, you can find the value of beta at that point by just taking the collector current dividing by the base current. So on the previous curves, we would just take ICQ and divide by IB3, which was what was the operating point, and we would get the beta at that point. And usually it stays pretty much the same for a DC circuit in the active region. It's not going to change a whole lot. But there is another kind of beta that sometimes is encountered, and that's the AC value of beta, which is the change in collector current divided by the change in base current. And most of the times, the two values aren't equal, depending on the situation in which you're using the circuit. So the DC value is typically used for bias circuit and DC design, and then we use the beta AC for amplifier small signal gain. However, all that being said, it is more typical to just use the one value of beta you're given rather than going back and forth between AC and DC. So in here, I will give you a value of beta, and unless certain conditions occur, which I'll explain in a minute, you will just use that for AC and DC circuits, because they're usually in the active region pretty close. In other regions, they may be real different, but in the active region, they're reasonably close. So in looking at curves, if we kind of stretch them out, and we just look at the first tenths of volts for VCE, you notice that we have an active region and a saturation region. The saturation region is stretched out a bit. And up in the active region, the AC beta value is high, like it is in the DC. It's 100, 200, something like that, depending on what type of amplifier you're using or what type of transistor you're using. There we go. The slope of the curve would be 1 over RO. And the resistance, the output resistance, is pretty high in that place. If we move to the saturation region, the AC beta value is low. And there's actually a specific resistance that you get from this, which is RCE saturation, which is just the saturation values, which is going to be different than RO. But it's hardly ever put into a circuit and used. So basically, this is just saying that the resistance in the saturation point is going to be way, way, way smaller than it is in the active region. So in the saturation region, the resistance of the transistor in that junction is going to be a few ohms to tens of ohms. And then in the active region, it's going to be really, really big. So most of the time, we don't worry about that too much. If we have a BJT in saturation, we can actually make an assumption about what model to use. And when we do that, it's actually just two voltage sources. There's 0.7 drop, which represents the PN junction, and there's 0.2 drop, which represents VCE and saturation. So the model is actually quite simple if you're operating in that region. Two more things that happens with BJTs. So this is all the theoretical part, and then next week we get to the actual circuits. As VCE gets bigger and bigger and bigger, all of the curves actually start to bend up eventually. And what is happening is the current is going up, but the resistance in the circuit limits the current, and it ends up heating the transistor and actually can damage it if it's run in this mode. So we tend to go below this breakdown voltage, which is called BVCEO. CEO stands for collector emitter with the base open. We don't even cover most, that was kind of thing we used to cover in Electronics 1 in ECET, all the ICBO and ICEO, and we don't cover any of that in here. So you don't have to worry about it. That's the one reference to something being open. All this means, all this says, I'm not going to tell you how to find this value. This value is listed on a spec sheet. Don't operate the transistor at a greater value of voltage than this. Don't set VCE to be bigger than what the transistor can handle. Yes?
Is there like some sort of type of BJT that's kind of like a Zener diode that's meant to be operated like that? And I don't see why you do that.
And I don't see how you could, because you kind of have to have the junctions biased in a certain way. Mm-hmm. So that would end up sort of making it upside down, or it would put it into it would basically put it into a cutoff mode. So yeah, it doesn't really work quite the same way. The last thing about beta, it depends on IC, and it also depends on temperature again. So if you have a situation in which beta is put at different temperatures, 25C is about room temperature, so you notice that depending on the current, the value beta goes up, and then it starts to decrease as you get to higher values of IC. And if you lower the temperature, you actually lower the whole overall value of beta, and if you raise the temperature, you raise the value up. And as I said before, if you look on a spec sheet, beta is actually listed as HFE, which has to do with two-port networks, which you study in circuits 2, I have been told. But I don't know if you do like H-parameter two-port networks or not, but that's where that comes from. It's just a type of H-parameter that comes from a hybrid two-port network, which basically is the output current over the input current. So that's, if you're doing a two-port network and you take the output current over the input current, that's what you get, is this HFE parameter. So that's all the theoretical stuff about BJTs.